Hello, you're welcome back. All right, so we're going to continue from where we stop. Okay, so now in this video, we're going to be looking at our circuit theorems. Okay, now previously we looked at the basic law in circuit analysis, which was Ohm's law. Okay, and we were able to solve some circuit, some network, okay, of resistors connected in series and then parallel. Okay, now Ohm's law, and of course, the analysis we did previously is actually limited to simple circuit. All right, now there are some complex circuit which you cannot solve by just applying Ohm's law or resolving the resistors in series or in parallel. Okay, there are some network in which you cannot actually resolve the resistors either in series or in parallel. So once you have such a network, then you require some advanced method and or some other laws that will help you to analyze such circuits. Okay, and that is exactly what we are going to be looking at in this video. All right, so now of course I will have to start with definition. So what's a circuit theorem? Now circuit theorem are simple the theorems that enable us to simplify complex circuit or network. Okay, for analysis. Right, so now these theorems actually go beyond just Ohm's law. Okay, now they help us to actually simplify complex network. Now, as you can see in this diagram, I have a network, right, which is made up of two voltage source, V1 and V2. And unlike what we treated before, right, what we are actually familiar with is just a network that have just one voltage source. But now I'm having a network that have two voltage source. Okay, so now circuit theory will help us analyze this circuit and of course to solve it. Now, what do we mean by solving a circuit or solving a network? To solve a network is simply to get the current across the components or the element of the network, the current and the voltage. Okay, so invariably if you're being asked to solve this particular network, right, you are being asked to find the current passing through each of the resistor and the voltage across the resistor. So that is exactly where the network theorems comes in. Okay, now this network theorem that enables us or this methods that we're going to be employing in this particular video to solve complex network, okay, will be either in a direct form or in a reduction form. It's either in a direct form or method, or in a reduction method. So if we are looking at the network theory that we apply directly in a direct method, okay, that simply means that we actually solve that circuit without changing the entire circuit. All right, we don't change it, we don't reduce the circuit to a simpler form, but we actually apply the laws or the theorems to solve the current and the voltage across the element of the circuit. But in a reduction form, okay, that circuit is actually changed or reduced to a simpler circuit before we can analyze it. So the difference is that direct form, we actually apply our theorems or to solve that circuit without changing the circuit. But in a reduction form, we have to change the circuit to a simpler circuit before we can now solve them. All right. Okay. So now there are some basic concept. Okay, you need to know before we actually start with the laws and the theorems. Okay, now the very first is already know what a circuit is, right? You need to know what a junction is in a circuit. Of course, for me to actually explain that, I will use this circuit here to explain all these parameters. Okay, you should also know what a loop is. Then you should know what a mesh is. Okay, you should know what circuit parameters. All right, so I think I'm gonna start. I'll start with the last parameters. Okay. Now the parameters of every of the circuit actually incorporate the values of the circuit element. Every circuit have element. Okay, depending on the component that is used in that circuit. Now, for example, a circuit that is actually made up of resistor. All right, the element of this circuit is resistor, and the resistor is being measured. Okay, in resistance. Okay, we measure the resistor based on its resistance. All right, so a circuit can also have another parameter. We can have this is a symbol of a capacitor, this resistor, and this is a capacitor. And the capacitor we measure the capacitance of the capacitor. All right, then a circuit can also have inductor. Okay, and we measure for an inductor we measure inductance. So once you have this particular component or element, all right, all these are the parameters of that particular circuit. So please take note of that. All right, then we are going to talk about let's look at what a junction is. All right, now you should know what a junction is. Junction is actually that point in a circuit where the current actually divides into branches. So in this circuit now, this point here, okay, I can call it point A. It's a junction because current that actually reaches this point A, as current flows from one of these source, as it reaches the point A, it will branch. Okay, it will divide into two branch. So um, this this part where this resistor R2 is connected is a branch, and the part through which the resistor R2 is a branch. So this junction, okay, where this point, junction or node, is the point where this current actually divides into branch. Okay, then the next is we need to it's a loop. Okay, so now loop is actually a closed conducting path through which current flows. Okay, or in a simple way, a loop is a path through which we through which current flows, right, from a point and probably return back to that particular point. Or you can define a loop is a closed conducting path in which we cannot, as we go through that closed conducting path, we cannot encounter any circuit element more than once. Okay, for example, this particular circuit now, if I should start from this point to move, okay, to actually to go through the direction of the movement of the current, I can go this way, okay, without branching, past this resistor R1, go through this resistor R3, then return back to the source voltage. That is a loop, okay? So that is a pathway through which current flows, all right? Starting from a point and returns back to that particular point. So we consider that a loop, all right? Okay, but um, a loop is said to be a mesh if and only if that loop does not contain uh, other loop, like what I just did. This pathway through which I've actually indicated the flow of current is actually a mesh. All right, it's a type of loop called a mesh. Now let me tell you why it is called a mesh. Now, okay, it's called a mesh because it is just a loop, okay, that doesn't have an other loop, okay, uh, within it. But if on the other way around, if I should actually trace, let's say I'm tracing the current to flow through this, to flow like this all the way, okay, then I pass pass through the junction goes all the way. So you now discover that this is not a mesh. This is I've just created a loop. I've just gone around a loop, all right, that contains two mesh. One mesh is the very first mesh, okay, is the one that I actually showed you before. Let me get so the loop I've just gone around contains two mesh. We have mesh one, this mesh one, and this is mesh two. Okay, so if that is well understood. Okay, so now as we go through the theorems, you get to understand these terms, this concept very well. Why? Because we are going to be making use of them. Okay, all right, so now let's start with the laws. Okay, so now we're going to start with the direct methods. I will have to. So in the direct method of circuit analysis, we're going to look at some laws, okay? And the laws, the very important law we're going to be looking at is Kirchhoff law. Kirchhoff law. Okay. Now this law is of two types. Kirchhoff stated two law. Okay, two laws. One of the laws is called Kirchhoff current law. Kirchhoff current law. Okay, which is abbreviated as KCL. Okay, you can also call this Kirchhoff junction law because this law is applied at the junction of a particular circuit. All right. Then the second law is is called Kirchhoff's voltage law. Okay, by abbreviation KVL. This law is also known as Kirchhoff loop law because the voltage law is applied across a loop. All right. So now we're going to start. We're going to go through them one after the other. So I will have to. Okay. I'm going up here. Kirchhoff current law. I'm starting with Kirchhoff current law. Here we are. Now let me state the law. Now according to Kirchhoff current law, okay, Kirchhoff current law states that the algebraic sum of the current that is entering or leaving a junction is equal to zero. The algebraic sum of the current. Okay, I've used this summation of all the currents. Okay, all the current that is actually entering or leaving a loop, leaving a junction, is equal to zero. And of course, you know what a junction is. So I'm using this particular diagram to illustrate. Okay, I have this current I moving and is coming to this junction A. Right now, from this junction A, I have three current moving away from the junction, and that's I1, I2, and I3. Okay, I can also okay illustrate that by drawing another circuit. Let's look at this typical example. Okay, so let's have a voltage source. Okay, now then there's a branch. Okay, so of different resistive components. All right, so let's say current actually flows from this source. As it reaches this junction, it actually divides, right? So this current is actually coming towards the junction. I call it junction A. It divides. Will have three different currents. Okay, let's call this R1, R2, and R3. So the current that is passing through R1, let me call it I1. This becomes I2, and this is I3. Okay, so according to Kirchhoff law, the if I should sum all the current that is entering and leaving, I is entering the junction A. As it enters junction A, it will branches. Okay, then I have I1 plus I2, I3 are leaving the junction. So now, another way of expressing Kirchhoff law is this. It's either you state it this way, right? That have the way I've already stated. The algebraic sum of the current entering, okay, or leaving a junction is equal to zero, or you state it this way. Um, the algebraic sum of the current entering a junction, right, is equal to the algebraic sum of the current leaving the junction. That is the way it's going to be equal to zero. It's like the law of conservation of current, if that actually makes sense, right? Remember, in the law of conservation of energy or the law, anything that have to do with conservation, okay, if the input is equal to the output, it will eventually yield zero. Okay, so the only reason I can say that the algebraic sum of the current entering into a junction is algebraic sum of the current entering junction and the algebraic sum of the current leaving the junction is equal to zero. The only way that will be possible, okay, is going to be possible if if we sum the current entering that junction or entering the junction, it should be equal to the sum of the current that is leaving the junction. So that way, I can also write the expression of Kirchhoff's first law to be algebraic sum of the current entering the junction, okay, should be equal to the algebraic sum of the current that is actually leaving the junction, going away from the junction, okay. So I is the current that is actually entering the junction A, and is equal to the sum of the current leaving the junction, which of course I will have to sum them. That's going to be I1 plus I2, then plus I3. Okay, so this is Kirchhoff's current law. So I hope that actually makes sense. All right, so let's now discuss Kirchhoff voltage law, KVL. All right, here we go. Kirchhoff's voltage law. Okay, I hope we are good. Now, Kirchhoff voltage law actually states that the algebraic sum of the current measured around a loop is equal to zero. Okay, the algebraic sum of the voltage or EMF measured around a loop is equal to zero. So, based on Kirchhoff's voltage law, I can actually write an expression for it. So, algebraic sum of the voltage all right, algebraic sum of the voltage measured around a loop is equal to zero. Already you know what a loop is, okay. Now let me actually let me draw a circuit to illustrate this. All right, so let's say I have a resistor, another resistor, three resistors, all connected in a series. This is a simple circuit, R1, R2, and R3 connected across a voltage. Okay, so if I should analyze our Kirchhoff voltage law, okay, it said that if I sum the voltage across this loop, okay? Now the voltage here, the sum of the voltage here includes this both the source voltage and the individual voltage drop across each resistor. This resistor will have its voltage, okay? Let's call it V1. This resistor will have its voltage, let me call it V2, and this resistor will have its voltage V3, okay? So if I should sum all of them, it should amount be equal to 0. So now the question is, how do you actually sum voltage, okay, that the values are not 0, then need to use 0? So which simply means that if that should happen, it means that some of this voltage drop will either be positive or negative. That is the only way it will be equal to 0, depending on the direction of the movement of the current. So now, if we should apply Kirchhoff's law to this particular circuit I've drawn now, we just, okay, let me clean up. Okay. Now, if I should apply voltage Kirchhoff's law, okay, in a simplified form, I will do this. Okay, I will simply say plus or minus V plus or minus V1 plus or minus V2 plus or minus V3. If you sum it up, it should be equal to 0. Now, why am I using plus or minus? As I said, depending on the direction of the current, okay, across that particular component, the voltage can be plus or it can be minus, and I will tell you some cases or situation that will warrant the voltage across a particular component to be equal to be negative, right? And that I'm going to show you. So the whole idea of Kirchhoff's law is to help us analyze complex circuits, all right, complex network that we couldn't ordinarily work or analyze using Ohm's law. Okay, so the example I'm going to give you now or in the next video will actually help you understand Kirchhoff's laws. Okay, so let's do that in the next video. See you in the next video. Thank you very much.